Math Ninja here. So I'd like to apologize for two things. First thing, sorry I haven't made a video for a while. The GREs. It's not fair. I study math. I don't write. So I had the writing section of my GRE test because it's a split test. So I do not have fair at all. I don't know English, I only know math. Because I only know math. And second thing, so I'm sorry about that. The second thing is I don't have my math outfit today because a typhoon just hit us. So the elevator is out. So I have to walk down 14 flights of stairs all the way over and up here to get here. I don't want to go down, back over, and up walking again. No, elevator broken. No. That's good exercise though. And math ninja needs an exercise. Anyways, so conjugacy. So I could cover both conjugacy and quotient groups today, but the thing is, conjugacy classes are just so important, so important. And quotient groups are also important, but you have to get conjugacy classes down. Because for a quotient, the form of quotient group, you need a normal subgroup. And a normal subgroup is the union of conjugacy classes. Typically, for example, they don't teach it as that. They give a different definition of a normal subgroup, and then derive an equivalence. But here, I think Armstrong was smart in having us learn conjugacy first. So, go Armstrong! Anyways, I would love to be there one day. Anyways, so I want you to do questions 14.1, 14.2, 14.3, 14.4, 14.5. You probably noticed that there's one question on isomorphism and 4 questions on how to compute conjugacy classes. I think computing it will help you remember better. I'm not a computations fan, that's correct. But I am a fan of learning things in whatever way possible. So this will help you on it. Computing conjugacy conjugacy classes of A6. Okay, good. Anyways, so you remember, so what's conjugacy classes? Well, you remember that we already did conjugacy as an equivalence relation. Remember, we say that A is related to B if and only if. So the relation is conjugacy relation. If only if there exists an X such that X or exists in G such that G of X, G inverse, or G of A inverse equals B. So two things are conjugate. If you can find some element such that G, A, G inverse equals B. For that, you can find one element G. So in other words, if you can find an element, just multiply both sides of G, such that G, A equals BG. So we can find an element such that when you multiply on the left by G, it equals the other element multiplied on the right by G. Okay, so that's the definition of the conjugacy relation. And remember, this is an equivalence relation, so we can form equivalence classes. So let's consider, for example, an abelian group. So every element commutes, right? So in an abelian group, notice that in an abelian group, G, A, G inverse equals, because it commutes, G, G inverse A equals A. So that means you only have A related to A. So every element, and you cannot have A related to B, A not related to B, when A does not equal B, or not equal B. So this means that every element is its own conjugacy class. You cannot have an element in there which is you cannot have two distinct elements be conjugated when the group is abelian. So important property, corollary of this is corollary every subgroup of an union is a union of conjugacy classes. And of course, we have classes that subgroups that are not union of conjugacy classes. Remember, this is only because each element is its own conjugacy class. So, just for example, let's compute the conjugacy class of D6, the one number D6. Right? Okay. D6, the Hebrew root of order 6, is equal to, we have the identity, we have R, we have R squared, we have R. No, R squared, S, or RS, and RX, and R squared S. Okay, D6, right? So, alright, we want to say when you multiply, let's look at the first powers of R. Let's look at the conjugacy classes that relate to R. Okay, so notice here that when you take an element, so we want to look at everything in the form G. Let's say any power of R. Go to 2. So let's say, let's look at R. And let's conjugate to R. So G, R, G. Yeah, the book gives you more general arguments, but I'm too lazy. So let's say, so G has to be the form S to the, or let's say R to the S, R to the I, times S, R to the I. Oh, did they do D6 or D12? Oh, they do even better. They do. Oh, I'm sorry. I got confused with Armstrong notation. Armstrong, they use D6 to talk about a group of order 6. Here, they talk about D6 as the Dihedral group that has 6, that represents one sort of a plate of 6 sides. Okay. Look at that. Okay, next time that I'm confused like this, you stop me right away. That's what I tell my kids. Like, they are not on YouTube. So, I mean, that's what I tell my kids when I teach. Stop me whenever I make a mistake. So, R squared, R third, R fourth, R fifth, SR squared, SR cubed, SR4, and SR5. So this is the group of order 12. They create S. Yep, I've got S. S. Okay. So let's look at the first, let's say, the things that are conjugate numbers of R. Okay. So what's conjugate powers of R? Oh, let's check. Suppose you have an element R, for example, R squared. So R with some power. Then we know, multiply it on the left and right by an element of G. So one that what's conjugate to Ra? So GRA. So you multiply both sides by some elements represented by S, T, I, R, B. Okay, well, let's say there was no X first. Well, by conjugacy, we know this guy's equal to RA. So trivially, RA is related to RA. Duh. Secondly, we know, so now let's try something that's not trivial. SRB, or SR